Hello and welcome. My name is Cato Fallon, and this is the presentation I gave in defense of my research that I completed at Indiana State University. The successful defense, which occurred in November 2025, was in partial fulfillment of the requirements for the Master's of Science degree in Geoscience. This is a recording of the presentation that I made after my research was defended. Before I begin, I would first like to acknowledge my committee members, Dr. Alex Elvis Badillo, my committee chair, Dr. Brooke Drew, and Dr. Jeffrey Stone for their time and commitment to my research. I have an interesting story to tell you today, and I am very excited to share it. This is the story of my research into the analysis of volumetric reconstruction methods in archaeology. I have much to say about my work, so my presentation will follow this agenda. I will first discuss the background to my project. This concerns the archaeology of Pompeii and an introduction to structure from motion photogrammetry. Next, I will describe my research questions and introduce my hypotheses. I will then explain a preliminary test that I performed to understand the accuracy of my readings. Finally, the rest of my presentation will concern the methods, analysis, and discussion for my respective hypotheses. All right, now that you know what is ahead, I invite you to sit back, relax, and enjoy my presentation. My story begins at the archaeological site of Pompeii. Pompeii was an ancient port city located in Campania, Italy. Something that I didn't know about Pompeii when I first started working there was that it has a centuries-long history beginning in about the 8th century before the Common Era to 79 CE, where it was famously destroyed by Mount Vesuvius. The volcanic processes that destroyed the city preserved vibrant frescoes, detailed mosaics, unique objects, and architecture, leaving behind a remarkably complete archaeological record. As a result, one of the most complete pictures of life in ancient Rome is able to be reconstructed. Pompeii was designated a UNESCO World Heritage Site, owing to its exceptional preservation of Roman life. Today, the archaeological park is visited by millions of visitors every year, attesting to its unmistakable significance to human history. I've included here a couple examples of the ways in which frescoes, mosaics, and architecture were preserved. In the top half of the screen, I've included some of my favorite examples of the frescoes that I found around Pompeii. These include depictions of cherubs performing various activities, including riding crabs. I've also included an example of a famous depiction of Alexander the Great in the bottom left. He's depicted in a highly detailed mosaic that covers an entire floor. Every time I see it, I am so impressed with the craftsmanship of this particular mosaic. I'm grateful that I wasn't the one who had to place each individual piece of the mosaic. In the bottom right is an example of the architecture that you can find around site. I tell everybody that I talk to about Pompeii that it is truly an entire city that was covered by volcanic ash. And so you can see this entire city from various vantage points around site as it sprawls out below you. From this particular perspective, I'm on a guard tower in the north part of the city looking south. In addition to being famous for its stunning picture of Roman life, Pompeii is also known for being one of the oldest archaeological sites, having been systematically excavated since 1748. Historically, these excavations have emphasized the removal of the volcanic material in order to unearth the city as it existed in 79 CE. Few projects have explored what lies beyond the 79 CE layer. And this is important because these projects add insight into the architectural and cultural changes happening in the city throughout its long history. On the right here, you can see an example of a part of the building complex that I conducted my research in. And you can see how much volcanic material had to be removed just to uncover the ruins of Pompeii. And this is the type of removal that the excavations have been prioritizing. They uncovered the city as it was at a specific time, but the history of this city is centuries long. And so it's important to study how the city developed and changed over time. So now I will take us to the southeastern corner of the archaeological site, to Region 1, Insula 14, to a small building complex located on the southern half of this insula. This is where the Pompeii I.14 Project has been conducting research since 2022. This project investigates the pre-eruptive history of Pompeii, exploring how ancient spaces grew, functioned, and changed over time. And the work from this project is important because it has highlighted the complex interactions of social, political, industrial, commercial, and domestic expressions within the space and how they've changed over time. And this is important for not just understanding the particular space, but the city of Pompeii and the region as a whole. Important to the Pompeii project is how much it embraces digital technology. And it has to embrace digital technology for a number of reasons. And these reasons are due to the challenges associated with a dense and urban excavation. So, because you have centuries of history, centuries of development, all in tight spaces, you have very complex stratigraphy, you have a large volume of finds. And in the case for this project, where archaeologists associated with this project are located not only around the United States, but the world as well, there are difficulties accessing and sharing data. So, a series of digital data collection forms and the use of structure from motion photogrammetry was employed to enable the project data to be accessible to staff, visualized in real time, standardized, and easily shared. Important to my project is structure from motion photogrammetry. Structure from motion photogrammetry concerns the production of 3D geometry from a sequence of 2D images. And it's been widely used as a digital recording tool to accurately capture architecture and archaeological trenches. In the top left side of the screen, you can see how a series of overlapping images represented by these blue square polygons are able to generate a point cloud. And from the point cloud, a solid 3D geometry can be formed. And this geometry is appropriately scaled and georeferenced and can be made very accurate to within about sub-centimeter accuracy. From this geometry, a photorealistic texture can be applied, and this gives archaeologists a 3D documentation of their excavation trench from a particular moment in time. And so the final data output from each field season concerns digital reconstructions of every excavation trench compiled using sequences of progression models captured from structure from motion photogrammetry. The image on the bottom here depicts these progression models. We're able to see an entire season of archaeological excavation in one place. And special about these progression models is that you can peel back the excavation like an onion or a layered cake, and you can visualize the excavation trench as it appeared at a specific moment in the excavation. And so by putting this into a 3D web scene, archaeologists from anywhere in the world can visualize their archaeological trench from a given excavation season, from a given moment, and have documentation of their archaeological trench. Important also is Agisoft Metashape. This is the software that we used to perform photogrammetry and create our photorealistic models. This is an example of what it looks like to perform structure for motion in the field. That's me trying to capture the archaeological trench from all possible sides in order to get the most robust geometry of the archaeological trench. So I've described how the 3D models of archaeological trenches have been used primarily as tools to document the stratigraphy of sites and to capture various archaeological deposits and architecture. Since about 2021, though, there have been a few projects that have explored and demonstrated the ability to use photogrammetry models as analytic tools, mainly through the use of reconstructing soil volumes. And this has been done for a number of reasons, primarily to obtain information on artifact densities or to visualize destroyed contexts. I'll describe that in a couple of slides here. What's important is that two methods have emerged for creating volumes using photogrammetric data. They both work by creating a manifold mesh that incorporates a top and a bottom progression layer. And when I describe a manifold mesh, I am describing a whole mesh with a top and bottom progression layer that has no holes, no seams, and is considered watertight. So if I were to submerge a manifold mesh into a bucket of water, no water would be able to get into the mesh. And so this allows me, when there are no holes or no seams, to calculate the volumes of these meshes. Important also is that both methods to reconstruct volumes are accurate to within about 3% of the original deposit. Method 1 of volumetric reconstruction uses the software CloudCompare. CloudCompare is used for processing and analyzing 3D point cloud data, and it is also capable of working with triangulated mesh data as well. It is crucial for calculating the distance between point clouds and meshes, or point clouds and point clouds. It is also able to reconstruct 3D surfaces from point clouds. So the main digital tools used from method 1 of volumetric reconstruction concern the filter points by value tool, which you can see being implemented up top, and the Poisson reconstruction plugin, which you can see being used on the bottom of the screen. The filter points by value tool is significant because it is able to essentially filter out points that have been, assigned distance from other points, and it can isolate points that are farthest from each other, and it can isolate points that are closest to each other. So you can see from this example that I've provided how overlapping points have been identified and then later removed. Um, the points that have been removed are visible in the top right, in the volumetric space that is left from these overlapping points that have been removed is visible in the bottom there. And so this allows me to visualize and identify the volumetric space between two models. There are clearly some points there that are left. The volume is not fully isolated, so some manual work will need to be done, but largely the volumetric space was isolated and overlapping points are removed. That's the most important step. And then you can see on the bottom how point cloud data was converted into a triangulated mesh from which a volume can be obtained. That's the Poisson reconstruction plugin in action. Method 1 has been the most described method of volumetric reconstruction in the literature, being demonstrated by multiple archaeologists and being applied to a few projects in the field already. Method 2 of volumetric reconstruction uses Agisoft Metashape and Blender. Blender is a computer-aided design software that supports the creation, modification, and analysis of 3D models. Volumes in Blender can be calculated using its 3D print add-on, which I think is a very clever way of using the tools for a program that is otherwise designed for creating bespoke 3D models or animations. However, the important digital tool that Method 2 uses is the remesh modifier. And the remesh modifier is the tool that converts two progression models into a manifold mesh. And this method hasn't been demonstrated that much in literature, but there's some precedent for this method. On the right here, I've included examples of the types of remesh modifiers that you can use within Blender. The unmodified mesh is visible on the top left, and then you can see how the morphology of the model changes based on the type and resolution of the various remesh modifiers. For my study, I chose to use a smooth remesh modifier with an octree depth of 8. Octree depth just determines the resolution of the morphological reconstruction. It concerns the amount of subdivisions of polygons that occurs within the remeshing process. And so represented here is an octree depth of up to 5. I used an octree depth of 8 just to make sure that the larger models that I used were the highest resolution possible without destroying my computer. So there are numerous applications of volumetric reconstructions to cultural heritage, various industries, and environmental science. With respect to cultural heritage, many reconstructed volumes have been created to obtain information on artifact densities. And obtaining information on artifact densities is important for understanding the formational histories of various archaeological trenches and archaeological sites as a whole. Energetics can also be calculated from volumetric reconstructions, and this is important for understanding ancient labor organization practices. If we're able to calculate how much material went into the creation of a particular structure. Volumetric measurements are also important for visualizing and quantifying what threats there might be to various archaeological sites. The amount of degradation that occurs to an archaeological site due to foot traffic, erosion, or other threats can be monitored through volumetric measurements. And also important within cultural heritage is the ability to visualize excavation sequences and the ability to reconstruct the pre-excavation state of excavation deposits. This is highly important because archaeology is inherently a destructive discipline. There are also various applications for volume calculations to meet industrial needs. These needs are most commonly related to the measurement of materials and resources. This is important for understanding how much of a given material is being stored in a certain stockpile. The mining, quarrying, and construction industries all depend on the accurate measurement of materials to manage project sites and understand the flow of resources. Photogrammetric data is already being used by these industries to calculate the volume of resource stockpiles and measure the morphological changes in size of quarries and mines. Photogrammetric data has also been used to measure and monitor the volumes of truckloads of forestry material. From the investigations I have done into the applications of volumes, there is a clear need for volume measurements for various industrial purposes. Photogrammetric data has also been used to calculate the volume of coral in order to study the biodiversity and ecological health of underwater ecosystems. Similar data has also been used to monitor landfills to see how they have changed over time. There are numerous applications of volumetric measurements beyond cultural heritage. So I've demonstrated that there is a need for volumetric workflows and that there are two acceptable methods of visualizing and quantifying soil volumes that already exist. There's been no discourse on the ways that the software choice affects aspects of the output, such as the volume quantifications or morphology, or aspects of the workflow, such as time efficiency or storage space needs. So in order to fill this intellectual gap, I propose an analysis between the two discussed methods of volumetric reconstruction that demonstrate the best practices of creating volumetric data and that inform the strengths and the weaknesses of each method. I would now like to introduce the questions and hypotheses that I explored during my study. So the main question that I sought an answer to was, how did the methods of volumetric reconstruction in Blender and CloudCompare perform with respect to deviation, reproducibility, efficiency, and scalability? Deviation concerns the differences between volumetric and morphological output between Method 1 and Method 2 workflows. Reproducibility addresses how much of a productive process each workflow is, while efficiency discusses the costs associated with the time to complete each workflow, and scalability addresses whether a particular method is better applied to datasets with larger quantities of progression models. For hypothesis 1, the question that addresses this is, are there any significant volumetric or morphological differences that arise between digital outputs? And I hypothesize that the volumes created through Method 1 will deviate the most relative to Method 2 in a comparison of volumes and morphological distance. And I chose Method 1 to deviate over Method 2 because in previous studies, data that was processed through Blender or Agisoft Metashape was the most accurate relative to other volume reconstruction methods. Agisoft Metashape also produces high-resolution mesh data, which I think will give Method 2 an edge over Method 1. Hypothesis 2 concerns reproducibility, and the question here is, how much does the software itself influence the output? And I hypothesize that Method 1 will yield the most reproducible output compared to Method 2. And this is due to the filter points by value tool in CloudCompare. Having predefined thresholds that isolate the volumes to a very high degree, I think will allow this process to be much more reproducible than the more involved processes involved in Method 2. Hypothesis 3 concerns efficiency, and I ask, how much time does it take to complete each workflow? And I hypothesize that Method 1 will be more time efficient than Method 2. And this is because of the digital tools in CloudCompare that reduce the amount of guesswork and interventions that are involved with Method 2. Hypothesis 4 is researching scalability. And for this, I ask, how storage intensive is each method? And I hypothesize that Method 1 will demonstrate that it can be best applied to larger projects over Method 2. And while Method 1 and Method 2 have both been tested in the field, the reliance on photogrammetry models as the input data for Method 2 will make it a more data cumbersome method compared to Method 1. And so now let's move on to the preliminary experiment that I performed. And the reason I performed a preliminary experiment is because I wanted to test the accuracy of the volumetric reconstruction methods. And even though there has been previous research that has been done on the accuracy of volumetric reconstructions, I wanted to specifically test Method 1 and Method 2. So the question for this research was, are the volumetric workflows accurate? And my objective was to compare the volumetric measurements made using Method 1 and Method 2 to a known volume that I calculated and measured myself. And so the most direct way that I could do this was by measuring the volumes of different boxes that I was able to obtain. You can see my setup there on the right. I was able to include scale bars to allow my models to be highly accurate. And I also included GCPs on each of the 4 edges so that I could align the models to like a base model, just like what we were doing with the Pompeii dataset. This screen here shows the various dimensions of each box and their respective volume. I won't address the volumes of each box individually, but I would like to point out that each of the volume produced from the direct measurements is very similar to the volumes produced by Agisoft Metashape, Method 1, and Method 2. I would like to point out here that I was able to use Agisoft Metashape to calculate volumes in this case because the models that I was working with, the boxes, um, they allowed me to very easily close the holes along the bottom of each box. This is not something that Agisoft would be able to do for archaeological trenches at a much larger scale, but for more simple objects, Agisoft Metashape was able to calculate volumes just for this case, just because the objects were simple. But yes, the volumes and the measurements are very closely related to each other. And these measurements, with using these measurements, I was able to show that the volumetric reconstructions using photogrammetric data are accurate to with around 3% of the measured volume. And so this shows that the volumes produced using the Pompeii data set are going to be accurate to within about 3%. And that this is also important because they build consensus with previous studies that examined the percentage errors of volumetric reconstructions to known quantities. The results also pointed out that volumes produced using Method 1 and Method 2 deviate little from the photogrammetric input. This just means that having a robust photogrammetry data set is going to result in a robust volumetric calculation. Finally, Method 2 appears to be produce more slightly accurate volumes, but just slightly. And we will see more on the results of Method 2 compared to Method 1 later. Now it is time to discuss my methods and data collection. This is the volumetric workflow that I performed. While it looks like a lot, there are only a few crucial steps that I would like to point out. First, I would like to point out that obtaining georeferenced progression models from the structure for motion processing workflow is imperative for having aligned models to merge together and turn into volumetric layers. Method 1 and Method 2 would not be possible without georeferenced meshes. Second, I have included in bold the important steps for Method 1. This includes the filter points by value tool, the segment overlapping points tool. These tools allow me to get rid of any of the overlapping or extraneous geometry and are a more simple way to apply predefined thresholds to remove these types of geometry to isolate a volumetric space. And then I've also included in bold the Poisson surface reconstruction plugin, which converts the point cloud data into a triangulated mesh. From this procedure, I can calculate the volume. In Method 2, you'll notice how this method is more reliant on Agisoft Metashape. Agisoft Metashape was used to merge models together and to isolate the volumetric space. However, after this was done, the models were imported into Blender so that they could be remeshed and have their volumes calculated. Blender is only really useful for this remesh modifier, and it's not a super involved software, but it is how the models can be turned into manifold meshes, and it's how their volumes can be created. The data that I chose to analyze and produce volumetric layers from are as follows. I chose two various archaeological areas from the Pompeii I.14 Project. I chose this data because they have these archaeological trenches have a variety of archaeological deposits of varying size and complexity that I could use to test the rigors of the volumetric reconstruction workflows. There are 15 progression layers between these two different archaeological areas, and so that there will be 13 volumetric layers. I also chose these two archaeological areas so that I could compare the differences between an archaeological area that does not have a lot of progression layers versus one that does. Now let's jump into how I tested for hypothesis 1 and how I chose to represent deviation. So to test for deviation, I separated this into two parts. The first part concerned a volumetric calculation comparison, and for the second part, I chose to do a morphological comparison. After quantifying the volumes of manifold meshes from method 1 and method 2, I performed a paired t-test to test whether the volumes I calculated are statistically significant, whether or not their differences are. This analysis was chosen because I sought to determine the difference between pairs. The morphological comparison was more complicated, as all of it had to happen inside of CloudCompare. Both manifold meshes made through method 1 and method 2 were imported into CloudCompare. A cloud-to-mesh distance function was applied to measure the distance between each model's vertices. I then recorded the quantity of overlapping and deviating vertices. I also chose to include the signed differences in this cloud-to-mesh distance function in order to capture the direction of any differences that occurred. And so for the analysis, I recorded the quantity of these overlapping and deviating vertices, whereby overlapping vertices deviated by less than a centimeter in any direction, where positive deviations included greater than a centimeter difference in a positive direction, and negative deviations were greater than a centimeter difference in a negative direction. I would also like to point out that in this comparison, the blender or the method 2 meshes made using Blender were the reference model. All of the method 1 models were the compared model for this morphological comparison. So the results of the volumetric comparison are as follows. The volume quantifications look similar, but they are a little different. You'll notice that on average, method 1 volumes are a little bit higher than method 2 volumes. And while these differences appear to be small, the difference between these two methods are statistically significant. I've included here examples of the range of these differences, so you'll see that the calculations or the quantifications made through method 2 could be less than 1% of difference, but they could be as great as 26% different from each other. And you'll see the two layers that are the closest and also the furthest from each other. But they're pretty similar. They tend to be pretty similar regardless. Here are the descriptive statistics for the paired t-test. You'll see that they're barely statistically significant, and that, on average, method 2 models are smaller than method 1 models. And so from this comparison, I want to know why these volume quantifications are statistically different. And I think the morphological analysis may give us some clues. So these are the results for the morphological comparison. They show how method 1 mesh geometry compares directly to the mesh geometry of method 2 models. I'd like you to focus your attention to the right side of the screen. This shows how similar each volumetric reconstruction is to one another. You'll notice that overlap ranges from 66% to 97%, and on average there's an 84% overlap. Observe how the models deviate as well. There tends to be more positive deviations than negative deviations. This shows that the mesh morphology of method 1 models tends to deviate positively from the mesh data made through method 2. Here are the visualizations of how these deviations can be visualized. On the right is an example of the reference mesh I made using method 2 in Blender. You can see how it preserves the complex geometry of the corners and edges. On the left is the geometry of the method 1 mesh, with a scalar field applied to highlight areas of positive deviation. The overestimations and deviations appear to manifest themselves as large bubbly geometry, likely caused by areas with low data resolution or uncertain data. Notice how well the Blender mesh captures the complex morphology of the edges, corners, and thin deposits. I've included areas that correlate to similar parts of the model between the compared mesh and the reference mesh. Here's another example of how CloudCompare reconstructions compared to Method 2 geometry. The bubbly and uncertain geometry is the most evident here. This is further proof that Method 2 models can capture complex shapes well, whereas there appears to be some struggle in reconstructing mesh surfaces in Method 1. The results from this analysis show that relative to Method 2, there are consistent overestimations of Method 1 models in not only volume, but generated mesh morphology as well. Here we can see the entirety of my results. Remember that green indicates overlap, red indicates positive deviation, and blue indicates negative deviation. These images show how models for Method 1 most consistently have positive deviations present. The frames highlighted in yellow indicate the volumetric layers with the least overlap. With the least overlap. Each of these highlighted models has an overlap of less than 80%, with the lowest overlap being 66%, as seen in archaeological area 19,000, layer 5. It should be in the middle right there. The frames highlighted in green indicate the volumetric layers with the most overlap. Each of these highlighted models has an overlap of more than 95%. From these models, you can see how the variety by which Method 1 models conform to the morphology of Method 2 models. If you want, you can pause the video here to look at each model more closely. Now it is time to discuss the data collection, analysis, and results for Hypothesis 2, which concern reproducibility. The analysis for Method 2 concerns the assessment of how much of a productive process each workflow is. To capture this, I am measuring moments of intervention that I will refer to as MOI here on out. MOI are subjective decisions that influence the morphology of a model or a volumetric space. This does not include the predefined variables such as filtering points by value, octree depth, etc. In order to collect data for MOIs, I recorded all of the processing that I completed so that I could revisit each screen recording and tally up how many times I intervened in the definition of the volumetric space. I also performed the paired t-test to test for the significance between the results for Method 1 and Method 2 models. Here is a comparison of how I measured MOIs for Method 1 and Method 2. You'll notice that Method 1 MOIs are a little bit more deliberate, and I don't have to do as many compared to Method 2. You'll see that by the time I complete a single MOI, I've already completed 4 for Method 2 compared to Method 1. And the results for this difference in number of MOIs that you can visualize here, and that you need a lot more for Method 2 than Method 1, is visible in the results here. These are the results that I was able to tally between each volumetric layer and each corresponding method. You'll notice that significantly higher MOIs for Method 2 are needed than for Method 1. You'll also see that Method 1 ranges from 3 to 17 MOIs, whereas Method 2 ranges from 9 to 39. Method 1 also averages 6 MOIs, while Method 2 averages 23. This is a very consistent difference that is highly statistically significant. The only outlier is layer 7, and This is likely due to an incomplete progression model that made me have to incorporate a third progression model into the mix. But despite this, these results show that method 1 is the least productive process compared to method 2. For hypothesis 3, I sought to determine the time costs associated with the production of each workflow. And so I measured time internally using CloudCompare, Agisoft, Metashape, and Blender by looking at the timestamps on the console windows and exported files for each software in each export. For method 1, time started when I imported files into CloudCompare. The time ended when I calculated volumes from CloudCompare as well. For method 2, the time started when I merged two meshes together, and time ended when I exported a manifold mesh from Blender. This is because internal to Blender, it doesn't have a very good or robust console window, and it didn't record when I calculated a volume, so I had to look at the exported file to determine when the workflow was completed. These are the results for hypothesis 3. They're very similar to hypothesis 2 in that there is a very clear difference between the results of method 1 and method 2. Like the MOIs, method 1 is significantly lower than method 2. The average distance for these is about 90 seconds, which is surprising to me because this is not much individually. However, with more progression layers, that difference will add up. And this difference is statistically significant, showing that method 1 is significantly more time efficient than method 2. It is time to look at hypothesis 4, which addresses scalability. Hypothesis 4 examines the data needs of files associated with each workflow. To examine these needs, I created a very organized file structure from which I could separate files and determine storage space based on method in order to understand the needs of each method, and archaeological area to understand the differences in storage space needs from projects that use more progression models compared to fewer progression models. This is the final tally of all of the storage space needs of all of my related project files. I would first like to draw your attention to the method-based comparison. For reference, 1,000 megabytes is equal to 1 gigabyte. You'll notice that method 1 is more storage efficient than method 2 because method 2 consumes almost 52 times the storage space than method 1. This is likely caused by the need to work with Agisoft Metashape project files and associated progression models. The other associated working files do not cost nearly as much storage space as the progression models, as you can see by the other three highlighted squares, where the export files are all nearly identical in size. The difference is that method 2 requires two sets of exported files to complete its workflow, doubling its need. And this is because cropped models need to be exported from Agisoft Metashape and then later be exported from Blender. Now let's look at the archaeological area comparison. Archaeological area 19,000 consumes more disk space than archaeological area 21,000. This shows that more progression models matter for consuming storage space. The only difference from this trend is that the Blender project files and then the cropped model exports here consume more storage space. And this is likely due to the size of the 3D models of archaeological area 21,000 with respect to scale and resolution. Finally, I would also like to point out the storage needs of just the progression models that I derived my data from. They add an extra 7 gigabytes to my consumed storage space, bringing the total storage needs of my work to over 14 gigabytes. This shows that the progression models are a major contributor to the consumption of storage space. And now it is time to discuss the key takeaways from my project. The first key takeaway with respect to deviation in hypothesis 1 is that volume comparison showed that method 1 reconstructions overestimated the volume output relative to method 2 volumes. Similarly, the morphological comparisons showed that method 1 models tended to positively deviate from method 2 reconstructions. The combination of the higher volumetric calculations and positively deviating mesh morphology measured in method 1 derived data is enough to support hypothesis 1 and prove that method 1 deviates the most from method 2. For reproducibility, method 2 was demonstrated to be a more productive process, needing significantly more MOIs to recreate volumes than method 1. And this analysis was able to show that method 1 has a more reproducible output. This supports hypothesis 2. Just like reproducibility, efficiency and the related analysis shows that method 1 is a more time-efficient workflow than method 2. This supports hypothesis 3. It was shown that an average difference between method 1 and method 2 workflows is about 90 seconds per layer. This means that more progression models leads to more pronounced differences in time efficiency. And for scalability, method 1 was demonstrated to be more storage efficient than method 2. Method 2 needed over 50 times the storage space than method 1. In addition to this, archaeological area 19,000 consumed more disk space than archaeological area 21,000. More progression layers lead to more pronounced differences in scalability, as was shown from this test, and this supports hypothesis 4. The size of the data in both quantity and scale and storage requirements will ultimately determine the scalability, however. So, based on all of these findings, I have a couple of recommended applications for how method 1 and method 2 can best be used. For method 1, it was demonstrated to be very time efficient and storage efficient while also being not a very highly productive process. This means that it would be good for datasets with large numbers of progression models and good for quick volume quantifications. This would be good for projects that may have a strict timeline and or limited budget for the time spent by data specialists processing models. While it does deviate a little bit more than method 2 models, as long as the deviations are within acceptable ranges, this method would be great for producing a lot of very quick volume quantifications. For method 2, it was demonstrated to produce quality visualizations and volume quantifications. And it was also shown to best capture the original input data. This means that this method would be good for select volume reconstructions of singular deposits and good for volumetric layers that are complex and variable. Again, for method 2, fewer progression models are better for saving time and storage space. However, if this is not a concern, I think method 2 would be a good way to go. And finally, having worked with these workflows for a really long time now, I have a couple of proposed optimizations that I think would make method 1 and method 2 a lot stronger. For method 1, I recommend using dense point clouds, especially for smaller deposits. This would allow for higher data resolution to improve any uncertain mesh generation. This would come at the cost of increasing processing power and time associated with the workflow, but I think it would reduce the amount of uncertainty, and it would reduce the amount of bubbly geometry that was observed in these models. I also suggest maybe performing the cloud-to-cloud measurement immediately following the import of the point cloud data. I think this would make manual cleaning a more straightforward process and reduce the number of MOIs that you might need to complete the workflow. And for method 2, I found that it was entirely possible to eliminate Agisoft Metashape's role from this workflow, because as long as the models are aligned in space, they can be merged and have their geometry or overlapping or extraneous geometry removed in Blender. And so this would make method 2 more storage friendly and a more accessible workflow altogether. I would also like to indicate possible future directions for this work. The first is that I think it would be good to compare the volumetric workflows to measurements of volumes measured in the field to definitively know how well these methods work in excavation contexts, just because the measurements of boxes can be controlled for a little bit more than the complexities of archaeological trenches, and if there might be differences between those. That would be a worthy future direction. I also think that it would be good to explore methods to automatically remove overlapping and extraneous geometry. This would cut down on MOIs, and workflows could become more objective and less productive. My third proposed future direction is to combine the analytical and the visual benefits of each model. So far, I have described how the volumetric information of these reconstructions can be obtained and specific archaeological deposits can be visualized. But as of now, these two benefits are separate. You can have either one or the other. Being able to visualize and interact with the deposits and view their analytic information would be the most beneficial to their visual and analytic uses. And then my fourth future direction, which I would like to pursue, is to compare my proposed optimizations for each workflow to the methods used in this study. And this would show how much each method could close the gap with respect to MOIs, time efficiency, and time cost between the original methods and the optimized versions of Method 1 and Method 2. The study found that the methods of reconstructing volumes using photogrammetric data were significantly different with respect to deviation, reproducibility, efficiency, and scalability. Method 1 and 2 were shown to have different productive processes with different associated costs and benefits. These findings are relevant to current archaeological discourse by indicating which methods yield the best results and which methods create models efficiently. This is important for informing future applications of volumetric reconstruction using photogrammetric data. Finally, I would like to thank all of you who have been a part of my journey so far. I would first like to thank my advisor, Dr. Alex Elvis Badillo, for his guidance and mentorship. He has provided me with opportunities to grow and develop into the scholar and professional that I am today. I would also like to thank my committee, Dr. Jeffrey Stone, Dr. Brooke Drew, for their guidance and encouragement on my project and beyond. Special thanks to Dr. Allison Emerson and the Pompeii I.14 Project for involving me in 3 summers of research. I am grateful that I was able to collect and manage 3D data for this project and use it in my research. And to all the members of the Digital Data Initiatives team that I have worked with over the years, Courtney Bell, Gretchen Zoller, Eric Prendergast, and Katie Settle, you are all data rock stars. Thank you for contributing to my growth as a digital archaeologist and a teacher. And to the family, friends, and colleagues who have encouraged me along the way, I am very grateful to have had your support. Your encouragement made my work so much easier, knowing that I was not alone in my endeavors. Thank you. And thank you to the viewer for watching my video this far. Thank you for taking an interest in my work. If you have any questions or would like to open a discussion about volumes, I invite you to do so. I'll leave my email in the description should you need it. Thank you all.